Welcome to this tutorial on data and tools to model PV systems, everybody. We're happy to be presenting at the PyData Global 2021 and hope this content will shine some light into the amazing research that is going on in the PV world and showcase some of the cool projects which have an overlap of solar and data science, and also introduce you all to the some of the basic concepts of PV modeling via a Python package called pvlib. My name is Abhishek, and I will be presenting this content along with Kevin and Mark. Silvana unfortunately could not join the call, but she's actually one of them, one of the ones to spearhead this tutorial, and without her, this session would not have happened. So yeah, thanks, Silvana. Cool. So here's what we are going to go over today. The first section will offer some motivation for solar photovoltaics in general, and why do we need to model PV systems? Since the field is immensely growing, it's offering like very exciting data challenges, and I'll go over some of the interesting challenges the PV community has been trying to tackle using Python, machine learning, image processing, etc. Then we'll jump into the tutorials. So there are 3 tutorials in this session. The first tutorial goes over some of the very basic concepts and steps involved in PV systems, and basically we'll be introducing you to the Python package pvlib. The second tutorial will go over how much sunlight a PV panel receives, and then we'll wrap up with a third tutorial which shows how to calculate the power output of a PV system using a very basic model, but pretty powerful model called PV watts. Okay, so yeah, let's start with some motivation. So just in case if you're not in the solar bandwagon yet, solar PV installation has drastically increased in the last decade, as you can see in this plot. There are a few reasons for this. One of the main ones is that solar has become very economic, and actually it's even cheaper than fossil fuels in some of the cases. So that's why homeowners, businesses, and utilities have adopted solar in their portfolio. One of the other main advantage of solar PV is that it is renewable and clean source of energy. This means it reduces the greenhouse gas emissions, which are one of the causes for global warming. And another big advantage of solar is that it's very scalable. So you could have a small system as few as few kilowatts powering a small house, to hundreds of megawatts, which can power entire cities. So these are one of the few factors why solar has seen a drastic increase, along with some other renewable technologies out there. Okay, so with this increasing in penetration of solar, it has brought some interesting opportunities in terms of labor. So we can see the, from it's a plot showing how much contribution solar is giving in the percentage of the jobs renewables have. So humans have been researching efficient cell technologies, better way to construct solar modules, and smarter ways to install them, and actually provide O&M services for the PV systems out there. So all these different aspects of solar industry has kind of helped in increasing the labor. Okay, so this is a very interesting and very famous chart put together by NREL. It shows the amazing journey PV technology has taken in improving the cell efficiency. It just shows that there are there are many different kind of PV technologies out there. So One of the main ones is silicon, which is, as of today is having almost 90% of the market, but it's, one of the technologies out there. We have some other technologies such as the multi-junctions in purple. If you see in the right top of the chart, that technology has dominated the space applications where the cells are, almost like 47-48% efficient. We also have the thin film technologies, which basically is the line in the green. The lines in the green, they have captured a decent market share of 8 to 10%. Specifically, the cadmium telluride modules manufactured by First Solar. And then in the red lines, we have some of the emerging PV technologies. It's a different material based on perovskites. They have shown promising efficiencies, but we are currently researching on extending their lifetime and improving the reliability. So overall, this chart is showing a very nice and very interesting journey PV technology has taken over the last few decades. Right, so along with this improving efficiencies, the costs of PV systems have also come down drastically. The plots over here, show the cost of PV systems in dollar per watt. So it not only shows the significant decrease in costs of PV systems, but more importantly shows, how in PV system the module itself is one of the smallest costs. And so there are a lot of opportunities for cost reduction and improvements in other areas, such as the soft costs, making installation easier and more reliable, all the structural and electrical components, etc. Moving on. So this slide, is basically showing how wide the reach of solar is actually. So right from the basic science, which involves, research in materials and chemistry to make better materials for PV cells, to module manufacturing, which involves, fields of optics, electrical engineering, mechanical engineering, the construction of huge PV systems. And there are like a lot of fields, which solar, touches. So there's huge scope for kind of collaboration out there. Fields not only from engineering and sciences, but also from humanities and business tie in for installations, adoption of solar, community adoption, etc. So this is just the tip of the field, and there are a ton of multidisciplinary topics of research that can be further explored. Renewables need smart minds from different disciplines to push the envelope on solar, such as solar plus. You have multiple other aspects which can be tied in with solar. So you have solar plus agriculture, which is typically termed as agrivoltaics, where you have huge lands filled with both solar and agriculture activities. You can look into machine learning, Internet of Things, electric cars, and storage itself. So I'm sure most of you would have heard of the Tesla wall, where we combine we couple the solar panels with the energy storage, and it can result into very interesting systems. All right, so let me just jump into some of the cool projects the PV community has been trying to tackle. So this is a very interesting project, taken by Kirsten Petty at NREL. It does the automatic recognition of configurations of the photovoltaic fields out there using machine learning. So she's using some very interesting image processing. The reason why we have to do this is, a lot of times we get production data for systems, but very little record of how things are actually installed on the field. And this is one of the cool projects which does that without any data available, just purely based on image recognition. This is another example of machine learning where we are using natural language processing to parse the field nodes of repair. So when the maintenance is performed, often there's not a standardized way to document the nodes, and this project basically leverages the power of NLP to predict how why we are losing the production based on the notes taken from the field. This is another cool project done by Silvana. She developed an open source program to use parallelization to perform ray tracing. It's basically optical modeling of how the light moves through from the sky to a PV system, and it's basically done to calculate the PV performance. Ray tracing is very computationally intensive, and this visualization just shows how it's done. This YouTube video is just kind of showing how the weather changes across the entire US. It's basically a time lapse of the year 2018, showing the top two figures are showing the resource, solar resource, and the bottom left is showing the temperature, how it's changing, and then the bottom right shows the wind speed. So the whole point is that there are like a lot of cool, interesting projects one can think about when it comes to solar and data. So this was just was to serve as a motivation to jump into some kind of PV plus data science activities. So with that, I think I'll just hand over to my my colleague Mark, who will help you to set up the Jupyter Hub basically to get started with the tutorials.
All right. So I'm going to paste this GitHub repository into the chat, and I'll also post it on the Slack channel. And we're going to scroll down to the README. Anybody can visit this site anytime. And once again, my name's Mark McCoskey, and the announcer already kind of gave my bio. So we're going to scroll down to the section that says tutorial setup. So these tutorials are designed to run in Jupyter. Basically, that's a way to run Python in a browser. And then we have set up a Jupyter Hub server at this address here. So it's a two-step process to get to these tutorials. First, what I need you all to do is visit the Jupyter Hub server, which I'm going to paste into the chat. So when you get to this site, you're going to see this sign-in image here. So put any username you want and any password you want. I think you can even leave password blank, but then you won't have a password. You can create new accounts if you need to. It doesn't really matter. So I already have one account, so I'm going to log in. So once you log in, you'll probably just see Scratch and shared data. So hopefully everybody's at that step. So click this link. You'll be shown this login screen. Enter username, password if you choose. And then the first time you log in, you will see Scratch and shared data. So you can give me a thumbs up, or if you have any questions, feel free to post them in the chat or in Slack. So then the next step is to click this next link here, which I'm going to paste in the chat as well. And this uses, whoops, that did not work. Let's try again. This uses a super cool open source project called NB Git Puller. Thank you. And what it's going to do is it's going to, now that you have this account created on our Jupyter Hub server, it's going to pull that repository, which I'm showing to you right now, this one, which is PyData 2021, into your Jupyter Hub environment. So if I paste this in here, you're going to see it syncing Git repository before sending you, and voila, here we are. Now we have the tutorial open. So let's see. After that, you're going to be in this folder page, and we're actually going to skip a few of these tutorials. One thing I wanted to say before is, I think I might have mentioned this actually already. So if you have any questions, ask in the chat here or also in Slack. And this is also being recorded. Okay, so I think we are going to go straight into tutorial 1. So I'm going to go back to my Jupyter Hub page, and the tutorials are numbered here. So this is tutorial 1. Okay, we're all on tutorial 1, weather data, accessing it and understanding and visualizing it. Just so you know, this server is running on an Azure virtual machine instance with 16 cores and 64 gigabytes of RAM. I honestly don't know how many people are attending, so hopefully we won't have any problems. I sometimes note that the pictures don't show up and this spins for a little while. If that happens, I just kind of stop and start it again, and then it seems to get them. Ta-da! Okay, so I think we are all good to go. One last thing I kind of wanted to cover is, as I mentioned, when you click this second link, we're using the NB Git puller, which pulls this repository in this branch. And this basically assumes that any changes you make in here are things that you want to keep. If you do make any changes to these, for example, today we're going to run these, so your output will change. Then when you go to run NB Git puller, it actually won't pull the tip of whatever the upstream main branch is anymore. So what you can do is go back here and just delete everything out of here. And as you saw me kind of quickly do it, fast way to do that is to open up this terminal and delete it using kind of Linux commands like rm, rf, pydata, blah, and it'll just be gone. So another quick, easy way to kind of get around that is just make a new profile. That'll work too. And there's really no limit to the number of profiles you can have. So, all right. So let me see the other things on here. There's also a Jupyter book document that you can access that has all this content. So after the tutorial, if you ever want to come back to this, it's all here. It's the same thing. And this will also point you to the Jupyter Hub or start a MyBinder instance or go back to the repository. And then you can also always run this on MyBinder here just by clicking this MyBinder link. And there's also instructions for running it locally. People may have to click the not trusted box and convert it to a trusted one in the top right of the notebook. Thank you, Abhi, to everyone. So yeah, so if anybody has that issue, trusted me executing. Yeah, I'm not sure if this is fully necessary. I've never done it, but if you want to do it, go for it. Okay, so with that, I'm going to hand it off to the next speaker, which is Kevin. Take it away, Kevin.
Yeah, thanks, Mark. Let me get set up here. So like Mark said, we're going to be starting with tutorial 1. And I already have this open. If you don't already have it open, then from the root of this Jupyter Hub, if you just click tutorial 1, it'll open it in a new tab here for you. So, and before we dive too far into the code here, I want to plug that PVLib has a Google group, and that's the sort of user support forum. And so if you're interested in using PVLib after this presentation, the Google group is a great place to be, and we're all very friendly and happy to answer questions. So in case in case this piques your interest, go check that out. So jumping right in, tutorial 1 is all about weather data. And probably unsurprisingly, weather data is quite important when you're modeling PV systems. Unlike sort of traditional generators like coal plants or natural gas or any of those, which, you know, if you run out of coal, you can just bring in more. Something like a solar farm is dependent on what weather is available. And if it's a cloudy day, then the system is probably not going to produce very well. So weather data is very important. People in the PV space spend a lot of time thinking about weather data. And so that's what this first tutorial is about. Accessing it, where you can find weather data sets online. Many of them are high quality and publicly available, even to hobbyists. Understanding what the relevant weather variables are. And so irradiance or sunlight is obviously a big one, but some other ones are relevant as well. And then, you know, how you can use this with existing Python tools. So scrolling down, oftentimes weather data is measured with these fancy, you know, space-looking instruments. These measure the intensity of sunlight in various ways. You can also get weather data from satellite-based models. So models that use imagery from weather satellites and then simulate what they think the weather was that corresponds to that imagery. Those are very powerful because they apply to many different locations. You don't have to have an actual weather station at the location of interest. And so there's a few different types of weather data in terms of how to produce it. Once you have some weather data, a very popular way of dealing with it in a PV modeling context is what's called a typical meteorological year. And the goal here is to solve the problem of every year is different when it comes to weather. And so for example, it's you know, October 29th, it's pretty sunny here where I am in Colorado today, but October 29th last year might have been cloudy, right? So obviously no 2 years are going to be exactly the same. And in particular, some years just might be a little bit sunnier than others just because there's a random weather variation. And so a typical meteorological year it's sort of a synthetic year in the sense that it never actually happened. This is not a specific year like 2020 or 2019. But a TMY is built from real data. And so for example, if you have 20 years of historical weather data, you look at every January, all of the 20 Januaries that you have on record, and pick the one that's kind of in the middle of the distribution when it comes to irradiance or sunlight or temperature or whatever else you're interested in. And you do that for every month, and you can assemble what's called a typical meteorological year. And so this won't reflect any actual year exactly, but it'll get you kind of close to a long-term average. And TMYs are really popular, and we'll be using TMYs for the rest of this tutorial. So I apologize in advance if I use too many acronyms. There's a lot of them in the PV world. I'll try to avoid them where possible. So like I mentioned, PVlib is a Python package. It integrates really well with the existing PyData stack. Especially it integrates well with pandas because of the nature of PV modeling is usually centered around time series data. And so pandas is a really convenient way to handle that. First up, we'll be reading a TMY, a typical meteorological year, data set using PVlib. And PVlib has functions for fetching data from a lot of different places, from different places on the internet, from reading various file formats if you have local weather files and things like that. The first one we'll be using is called read TMY3. And so TMY, again, is typical meteorological year. And 3, it's kind of like version 3 of the TMY file format. There's been a few iterations of it. You can think of it like that. And if you're interested in the documentation for this function, you can use the normal Python docs. We also have online sync docs on read the docs if you're interested in. And the idea is this is just reading a local file. You give it a file name, and then there's a couple of optional inputs you can use to make just change what it returns a little bit. And what it returns is a pandas data frame that has the time series data contained in the file. And TMY files also include metadata about the system or the weather station that recorded the data. And so if we look at some of the variables that are returned, no, this isn't rendering very well. Well, we'll look at this in a minute. So in this block of code, what we're doing is we are reading a TMY3 file that is actually shipped with PVlib. And so if you have PVlib installed, like this Jupyter Hub does, then this TMY3 file is already there and available for reading. And so this data dir is determining the directory or the folder that file lives in. And then we give that to this read TMY3 function built into PVlib. And we get back a data frame and a metadata dictionary. Uh-oh, Mark's telling me something. Yes, I will zoom in. Hopefully that's a little easier to read. So if we look at the metadata for this TMY file, TMYs are specific to a given location. And so a TMY file from one place won't necessarily be accurate for another place. This particular TMY was recorded at the Greensboro Airport, which is in North Carolina in the United States. And you've got some latitude, longitude, and some other metadata here. So this is the metadata available. If we look at the time series data that's in the data frame itself, DFTMY, then we can see some of the variables that are included in this data set. And one of them is GHI. And I'm gonna, again, stay away from the acronyms here as much as possible, but I'll note that the I here stands for irradiance. And irradiance is a fancy word for sunlight, basically. You have another one, DNI. Again, the I is irradiance. And then there's some other things in here, like pressure. You've got albedo, which is how reflective the ground is, basically. And in total, you can see that there's 71 columns. And so there's a lot of data in this file, and we're definitely not going to talk about all of it. 71 columns, and the other number here is 8,760. That's the number of hours in a year, assuming it's not a leap year anyways. And so you always hear in the PV world, everybody's always talking about 8760s, talking about hourly data sets that cover 1 year. So since it's a pandas data frame, you can manipulate it like you would any other pandas data frame. This is the PyData conference, so I'm going to assume that most of you are familiar with that. And again, here's all of the columns that are available. A lot of irradiances, DHI, the I is irradiance. You got things like dry bulb temperature, which is just the ambient temperature for that location, wind speed, and some other things that are relevant for PV modeling. Okay, so let's talk about irradiance. Irradiance is obviously the main driver of solar farm power conversion. And there's two main types of irradiance, and we have to model them separately. The first is what's called direct irradiance, which is light that's coming directly from the sun, and it doesn't get, it doesn't hit a cloud on the way. It doesn't get dispersed by aerosols in the atmosphere. It's basically, this is the light that when you look at the sun and you get your eyes burned, this is the light that's doing that. But that's not all of the light that is available for a solar panel to use. You also have diffuse light, which is coming in from the rest of the sky dome, is what we call it, just the rest of the sky. And so this is the light that makes the sky blue. This is caused by scattering off of dust and aerosols and stuff in the atmosphere. So some beam irradiance gets converted to diffuse irradiance that way. When I say beam, I mean direct. That's the same thing. On cloudy days, basically all of the direct irradiance gets converted to diffuse, because on cloudy days, you can't even really see where the sun is in the sky. And so direct irradiance must be basically zero. And diffuse irradiance is all there is if you're a solar panel. So these are the two components of interest, direct and diffuse, and we'll be modeling those separately. Wind and air temperature are also relevant, despite, obviously we're not talking about wind farms here. Wind and temperature are relevant because the operating temperature of a solar panel changes its efficiency. And the hotter it is, the less efficient the solar panel becomes. And so if you are interested in a very detailed PV model, then you're going to be modeling the operating temperature of the panel itself. And you have to model that based on the ambient air temperature, which you might get from something like a TMY3 file. And the wind speed. Wind provides a small cooling effect. So that's why wind and temperature are relevant. It's for determining the efficiency for each timestamp of your photovoltaic array. Okay, so down selecting those 71 columns down to the 5 that are really of interest here, we have 3 irradiance components, like I said, and these are various direct and diffuse sort of subcomponents of the overall sunlight. You have dry bulb, which is ambient temperature, and wind speed. And so these are measured, the 3 irradiance components are often measured in watts per square meter. And if that doesn't immediately make sense, then don't worry about it. But it's sort of a power density in terms of how much sunlight is available per unit space. And so if you multiply this irradiance in watts per square meter times the number of square meters of solar panels you have, then you can get an estimate of the total sunlight hitting your array. That's the idea. Dry bulb, ambient temperature is usually measured in Celsius, and wind speed is meters per second. So we can make some plots. I'm going to kind of blow through these fairly quickly here. Like I mentioned, so let's see, DNI. The D in DNI stands for direct. And so this is the direct component coming directly from the sun. And depending on these days, so this is a week of data here. On some days, the direct irradiance is basically 0. And on some days, it's really high, almost 800 watts per square meter. And so this is showing what days are sunny and what days are cloudy. And on the cloudy days, you basically have no direct irradiance. And all of the irradiance that's available to you is DHI, which is diffuse. And that's the orange line plotted here. And you can make fancy plots. That's all Matplotlib. To talk a little bit more about these irradiance components. So we've mentioned DNI and DHI. Those are the direct and diffuse horizontal components. You also have what's called global horizontal irradiance. And I don't know how important it is to really understand this fully, but the idea here is that you can measure sunlight in different ways, and it's useful for different applications. And so GHI, the global horizontal irradiance, is basically if you just point an irradiance sensor straight up and measure everything, direct and diffuse, then that's what GHI is. And the G is global, and that means everything is the idea, not just direct or not just diffuse. So this is sort of an all-in sunlight measurement. If you want to measure just diffuse, then what you do is you still point your irradiance sensor straight up, and you just put a little sunblock or a sun shield in between the sensor and the sun. And it's small enough that most of the sky is not obscured, but the direct irradiance coming straight from the sun is, and it gets blocked. And so in that way, you're measuring only the diffuse component. And if you flip this around, you can measure just the direct component by putting your irradiance sensor sort of at the bottom of a long, thin tube and pointing that tube directly at the sun. And so sunlight is able to, if it's correctly aligned, sunlight will go straight down the tube and hit the sensor. But diffuse light from the broader sky is not aligned with that tube, and so it won't make it in. So these are the different ways that these components are measured in practice. Okay. So here's some more plotting. I think we can safely skip this. The last up, I want to do just a little bit of comparisons on what you can use TMY data for, even outside of the context of PV modeling. And so, for example, if you want to calculate the total monthly sunlight for a given location to see how sunlight varies seasonally. And so, for example, in the Northern Hemisphere, at least in the US, we tend to get more radiance in the summer than in the winter. And TMY data is a really easy way to answer the question of, well, how much more do we get in the summer compared with the winter? And so, for example, since this is just a pandas data frame, it resamples very easily. And so we can resample to monthly and give the sum of each irradiance in each timestamp. And when we plot that, you can see that in the winter, at least for this location in North Carolina, we get even less than half of the irradiance of summer. We get less than half of that in the winter. So there's a lot of seasonal variation here. And to put this in context, back in the PV world, you don't just want electricity in the summertime. Generally, there's going to be some seasonal aspects to demand, but even in the winter, you still want electricity. And so when we are designing PV systems, we'll design it to kind of smooth this out a little bit, and maybe design the system in such a way that we will sacrifice some summertime irradiance to boost our wintertime production. And we'll talk about that some more in the next tutorial. We can also take monthly averages. And so here's comparing wind speed with ambient temperature. And so you can see that wind speed tends to be higher in the winter than in the summer for this location, which is cool because it means that wind power is kind of complementary to solar in a way. So when solar is producing a lot, maybe wind isn't producing so much, but when solar isn't producing, then wind is producing a lot. And so they complement each other in that way from a grid stability standpoint. And obviously in the summertime in this Northern Hemisphere location, temperature is higher in the summer than in the winter. So that's for all of this was done using a TMY3 file that ships with PVlib, but that's just one example file. And if you're interested in the Greensboro Airport, then great. Probably you're not, and you're interested in somewhere else. So let's talk about where you can get other weather data sets. There are many weather data sets available. Some of them are free, some of them are commercial and paid for. The one that we'll be using in the rest of these tutorials is what's called the NSRDB, which is the National Solar Radiation Database. And this is a weather data set produced by NREL in the United States. And it covers much of North America and some places outside of that, but it's not a global data set, unfortunately. This is free. You can sign up for an API key, and it's very easy to use. It's based on satellite, and so you can get it kind of anywhere within any location in this colored range is available in the NSRDB. But there are lots of other ones. We won't be using any of these in this tutorial, but they're worth mentioning just to let you know that they exist. Energy Plus Weather is more for building simulations for like air conditioning, heating and cooling type stuff, but it's also useful for solar modeling. PVGIS is a product that's really popular in Europe, and again is another free data source. Here are some other ones that are commercial. I think all of these are commercial. Probably they are. And so if you were financing a system and you really wanted to be sure that you're getting the best weather data, you might use some of these. Okay, like I said, we're going to be using the NSRDB for the rest of these tutorials. If you'd like to sign up for an API key now, it's very fast, and there's links in this notebook for that. If you don't want to do that now, then that's okay. And there's sort of a demo API key that's limited in certain ways, but we can still use it for this tutorial if you want. So I'm going to pause for a little bit here and to give people time to go and sign up for their key if they like. It's going to be just this string of gibberish characters that we copy and paste into a script later on, just to give you a heads up on that. Okay, let's see what's going on in the chat. I have been paying attention. Looks like Mark's been on top of this. Do those DBs come with coordinates, or do I have to get them elsewhere through an ID of the weather station or something? Yeah, good question. So for the weather data sets, like the NSRDB, for example, is based on satellite weather. And so there's not really any weather stations that contribute to that data set. It's all based on satellite imagery, or mostly anyways. And so the way that it works is, and we have an example of this in just a moment, you give it, when you make this request to the API, you give it a latitude and longitude that you're interested in, and it just gives you the weather data for that location. And so it doesn't have to necessarily be associated with the station. For databases that are based on actual ground weather stations rather than satellite data, then it's based on a network of stations, and each station has an identifier and coordinates, and you can look up the one that's closest to your location. So I'm going to assume that folks have an API key or are going to have one before too long. This cell, there's kind of a lot going on here. If you have an API key, then you can just paste it right there. And so you put it in single quotes. It's just a Python string. So, my key, it's not going to be English, but you can just put it in there as a normal Python string. If you don't have one, then there's, like I said, there's this demo key built into this notebook. You probably shouldn't be using this long term if you want to, if you're interested in doing this in the future, but just for this notebook, it's probably okay, and you'll get away with using that one. So like I was just saying, the function that PVlib ships with for accessing the NSRDB is called getPSM3. PSM is the physical solar model, and that's just one of the data sets provided by the NSRDB. And you give it a latitude and a longitude, the NREL API key that we configured in this cell above, the email that you signed up for the API key with, and then names represents what data set you're interested in. And so here we're going to be using a TMY, but the NSRDB also has single year data sets. And so, for example, if you wanted to model a specific year for a system, for example, to compare simulated production with maybe actual production from a real system or something like that, then you can request specific years. Like if I put 2019 here, then I would get back data set for 2019 rather than a typical meteorological year. So if we run this, then again, we get back a metadata dictionary about the location that our weather data applies to, and some other things like what units it's in, what version of the data set. This is very important. And then we also have this data frame of time series data, and this is called DFABQ. ABQ stands for Albuquerque, and this is for Albuquerque, which is a city in New Mexico in the United States. And it's just an example location. So now that we have our time series data, what we can do is let's compare it with the data from that airport in North Carolina that we were looking at earlier. And so monthly GHI, this was defined in a cell earlier when we're looking at seasonality. So that's still in this session. And we can compare it with our new data from Albuquerque. And so we're labeling this NC for North Carolina and NM for New Mexico. And so these are just two locations. North Carolina, you would expect to be less sunny than New Mexico, because New Mexico is in the desert Southwest in the United States. And so it's hardly ever cloudy there. It's very dry and very sunny. And the irradiance data that we have reflects that. And so again, NM is New Mexico here. So you can see that consistently across the entire year, New Mexico gets more sunlight per month than North Carolina does. And especially in the summertime, it's a very big difference there. And so this difference is why, I don't know if you know the history of solar deployment in the US very well, but the desert Southwest is really where a lot of the early initial deployment was for solar photovoltaics. And it's because there's just a lot more solar resource there to collect. But nowadays, now that systems are so cheap and so efficient, it makes a lot of sense to deploy them in other places like North Carolina, even though it maybe has less sunlight overall than the sunnier locations. Okay, so that's tutorial 1. Let's see, any questions here before we move on? I don't see anything in the chat. Cool. Okay, so at this point, we're gonna head on over to tutorial 2, which is called POA irradiance. I'll go ahead and open that one up myself. This one is all about taking these weather files that are sort of generic and not really tied to a particular PV system, and doing some modeling to generate the irradiance that is actually available for the PV system to harvest, you could say. And so POA irradiance, I know I said I'd avoid acronyms here. POA stands for plane of array. And this is it's the concept of the irradiance that's hitting your solar panel depends on where your solar panel is pointing, what part of the sky it's pointing at. And if you point it directly at the sun, then it'll obviously be getting a lot more irradiance than if you point it away from the sun. And so POA irradiance, what this tutorial focuses on is turning these 3 sort of generic irradiance components that we saw in the previous tutorial, turning that into the irradiance that's hitting an actual solar panel at a specific tilt and orientation. So this is the main driver of PV system power, is the plane of array irradiance. And so this is a lot of attention in the modeling world is given to getting this modeling process correct. Transposition is what this is called, is transposing these 3 base components into the plane of array irradiance. Okay, so like I said, the irradiance that's hitting your panels depends on where they're pointing in the sky. And so for any instance, depending on how well the sun is aligned with these 2 arrays, one of them is probably going to be getting more sunlight than the other one. And probably that's going to change not only across a day as the sun moves across the sky from east to west, but also seasonally, because where the sun is in the sky, basically how high it gets in the sky, changes with the seasons. And where I am in the Northern Hemisphere, in the summer, the sun gets high in the sky, whereas in the winter, the sun stays pretty close to the horizon. Even at noon, it's fairly low in the sky. And so the orientation of your panels affects production not only on a day-by-day basis, but also seasonally. And so, and this is what I was talking about with how well your panel is aligned with the sun. And so if you want to produce a lot, then basically what you're doing is minimizing this angle of incidence, the AOI, which is just a measure of how well your panel is aligned with the sun. And so if you minimize this angle, then you're pointing directly towards the sun as much as possible, and you'll be getting the most irradiance. So when I say orientation, what I mean by that is essentially it's defined by what's called the tilt and the azimuth. And the tilt is how far above the horizon your panels are facing. And so if they're just pointing straight up, then that's tilt equals 0. And as you tilt your panels more and more, eventually they'll be pointing directly towards the horizon. So the panel itself will be vertical. And that's at 90 degrees tilt. And typically the tilt is somewhere in between there, like 20 degrees or something like that. The other coordinate is called azimuth. And this determines where along the horizon your panel is facing. And so, for example, even if you're tilted at 20 degrees, for example, you can be tilted 20 degrees facing south, or tilted 20 degrees facing west or east or north or anywhere in between. And azimuth is a measure along the horizon of what sort of compass direction you're pointing. And so azimuth goes from 0 to 360 degrees. Technically tilts, it usually goes from 0 to 90. I mean, technically it can be tilted facing down. So I guess it goes 0 to 180, but nobody actually does that. And so you have, you measure your panel orientation with tilt and azimuth. And then you combine that with where the sun is in the sky, which is measured in a very similar way. Again, it's based on the azimuth, so where along the horizon it is, and then how high in the sky it is. You combine module orientation, panel orientation, with solar position, and then you can figure out what your POA irradiance is. And so we're going to be using that same TMY data set from before, just as an example. You could replace this really easily with a data set pulled from the NSRDB if you wanted to model a specific location, or you could use your own weather data pulled from somewhere else. The new thing in this cell is this location, which is a PVLib object that basically just encodes a particular location on the surface of the Earth, and it has some helper functions to generate things like solar position for that location. Okay, so we've got a location, and we gave it the coordinates that correspond to our weather data set, because obviously those have to match, or else things are going to get wonky. Next up, we calculate the solar position, and this is very easy. Just location.getSolarPosition. And then you give it a list of timestamps to calculate the solar position for. And if we look at the variables that are returned here, there's things like apparent zenith and zenith, apparent elevation and elevation, and then you have azimuth and equation of time. Azimuth, we already talked about. That is, again, where along the horizon, so what compass direction the sun is. Elevation and zenith are sort of complements of each other. They really measure the same thing. I think elevation is easier to think about personally. Elevation is how far above the horizon the sun is at this moment in time. And so you can see that all of these numbers are negative, which means that it's below the horizon. And if you look at the timestamps, it's because it's in the middle of the night. And so once this gets to dawn, elevation will cross 0, and then it'll go into the positive numbers during the daytime. And so you can think about elevation kind of the same way you think about tilt for the array orientation. Okay, so now, just recapping what we've done so far, we have the weather data for our location based on a TMY3 file. And now we've calculated solar positions for the same timestamps. And these are both data frames that are 8,760 elements long because they reflect a single year. So if we, the only thing we're missing here is the panel orientation, the panel tilt and the panel azimuth. And for this example, we're going to be assuming a 20-degree tilted panel with azimuth equal to 180, and 180 degrees is south-facing in the conventions that we use. So those are the three, really the three inputs here are the panel orientation encoded with those parameters, the weather data, these are the three irradiance components that we've been talking about, and then the solar position that PVLib calculated for us. And we give those three inputs, or sets of inputs rather, to this get total irradiance function that PVLib gives us. And we get back a data frame called DFPOA. And again, POA stands for plane of array. And so this is the irradiance that's in the plane of the array that we're simulating. And it's a data frame rather than a series because there are several components here. I mentioned that we model direct and diffuse components separately. And so these are each of those components after projecting it into the plane of array. POA global is the main one. This is sort of the all-in total in-plane irradiance. So this is what we're going to be using going forward. Okay, so what's the point of tilting your panels? That's a natural question that we get asked a lot. Like, why wouldn't I just put them flat on the roof? And like I mentioned, the panel orientation really has to match the solar position to get good production. And so by operating at a tilt, and again, this depends on where you are, north hemisphere versus southern hemisphere, and where you are, like basically your latitude. But for this specific location, tilting at 20 degrees facing south results in a fairly dramatic change, at least dramatic in my eyes, in irradiance. And so GHI, again, is sort of the base. That's the irradiance you'd have if you just laid your panels flat. But if you put them at a tilt, then you get these orange bars instead. And so in the wintertime, you get a fairly significant boost to production, or at least to sunlight collection. But it comes at a small cost in the summertime, because by operating at a tilt in this location, because the sun gets so high in the sky in the summertime, it's making the alignment worse in the summer by improving it in the winter. And so this is an optimization problem, basically, where you decide how much energy you want to produce at what times of the year, and then you can optimize your tilts to generate that desired profile. And because pvlib is a Python package, you can do this, you can just plug this basically straight into scipy.optimize or any of the other packages in the PyData ecosystem to do that optimization, which is really cool, because a lot of PV tools don't integrate with existing package ecosystems like that. And so that's really a strength of pvlib, is that it plays so nicely with I mean, not only pandas and matplotlib and all of that, but even more specialized packages like scipy. We can also make some more plots, and this is showing what I was saying, where this is a day in the winter, and you can see that the in-plane irradiance is a lot stronger than just the horizontal irradiance, whereas in the summertime, it's a much smaller difference. We can also model, so that was for a simulation for a fixed tilt and azimuth panel, and so maybe that's on somebody's rooftop or it's on fixed racking. But a lot of large-scale solar farms nowadays are using what are called trackers. And these are dynamic moving structures that change the panel orientation during, across the day to track the sun as it goes across the sky. And so rather than having a single tilt, like 20 degrees, for example, now you have a time series tilt and a time series azimuth that changes each timestamp based on where the sun is. And pvlib has a function to calculate the tilts and azimuths for tracking systems. Single axis, there's several types of trackers. Single axis tracking is the one that we'll be using today. And you give it the time series solar positions. And so again, these are time series inputs, and we get back a time series output. And now we have this tracker data frame. And if we look at this tracker rotation, you can see that it changes across the day. And in the morning, it rotates to negative angles, which means pointing towards the east. And then as the sun goes from east to west, you go into the positive angles, which means west facing. And then eventually you go back to 0 at nighttime. And so since the tracker rotation is changing, that means that the tilts and azimuths are changing to match. And like before, we use this get total irradiance function, and everything here is the same, except for the surface tilt and surface azimuth. And so now we have tilt and azimuth, which we just defined above. These are now time series inputs. They're pandas series that match our weather and solar position inputs. And so it's kind of cool that that pvlib is fairly agnostic to the things that you give it, meaning that this function works equally well with scalar inputs as it does with time series inputs. And if we look at how the tracker profile changes, or the POA irradiance changes with a tracker. So with a fixed tilt system, the POA irradiance looked more or less like the horizontal irradiance, but just maybe scaled up, like maybe multiplied by something. But with trackers, this is such a different thing that's going on, that you actually get better irradiance in the morning and afternoon than you do right at solar noon. Because in the morning and afternoon, you're able to face directly towards the sun a little bit better than you can at midday for a tracking system. But anyways, it certainly makes a very large difference compared to just laying your panels flat. And this is really the appeal of using trackers, right? Who wants moving parts in a big expensive system? This is why you want moving parts, because it makes such a huge difference in how much irradiance you can collect. Okay, so that's about all we have for tutorial 2. The next tutorial is going to be looking at converting, now that we have the irradiance input to the system, actually converting that into power output. But let's take a quick look at questions before we start that one. Cool, looks like I was maybe hitting some of these questions unintentionally.
Somebody asked approximately how much benefit do you see with or without trackers? And I was trying to think of what that might be, like off the top of my head. I was thinking like maybe 20%, but it's about broadening the shoulders, right?
Right. And wow, what a great question, because we happen to have an example. This is the PVlib documentation. We happen to have an example very much along these lines. Yeah, modeling transposition gain. So I'll just scroll straight to the output here. This is comparing monthly irradiance at various tilts for a fixed tilt system, and then also a single axis tracking. And so blue is just the horizontal irradiance as a baseline, and then the y-axis here is the monthly gain, so how much extra irradiance you get with each of these strategies. And so you can see that the brown line here is a single axis tracking one. And so yeah, it's about 20% fairly consistently across the year. Anybody else want to ask a question that we already have in the example gallery? Always nice to see that. What can be reasons to install panels that are not facing south, other than the southern? Okay, southern hemisphere is a good reason. If you are looking at rooftop systems, like a residential on somebody's house, then you're kind of stuck with whatever their roof is oriented at. And so if the roof is not facing south, then probably your panels aren't going to be either. For utility scale, large scale systems that are built on the ground, much of the time they are facing south. Probably the majority of fixed tilt systems that are big anyways and ground mounts are facing south.
If they're in the northern hemisphere.
Yes, northern hemisphere. Some reasons, even if they're on the ground and you wouldn't have them facing south, there are some farms that are built on like landfills, for example, or terrain that's just very weird and not flat. And if you have to match the terrain that you're building on to some extent, that's really the main reason that comes to my mind.
One more reason which I think of is certain utilities see their load peaking around 3 p.m. To 4 p.m. So they might orient their systems a little bit towards southwest. But again, that is for fixed tilt systems where the modules are not rotating. But for trackers, typically most of the sites will have south, will be south facing.
Is there degradation of efficiency of PV cells over time? Yes, and efficiency degrades in several ways. This is a little bit of a rabbit hole, so I'll try to keep it high level. Right, there's several different ways that degradation can happen. It's not just the cell itself, although the semiconductor part of a PV cell that can degrade in various ways. You also have things like the encapsulant that is living inside the module. That can degrade, and kind of browning is a common term for that because it discolors and starts blocking a little bit of sunlight. There's I don't know, you can talk all day about different degradation mechanisms. I think Mark said earlier that PV systems last decades, and he talked about warranty lengths. It's common to assume module level degradation rates at something like 0.5 or maybe 1% per year efficiency loss. And so, for example, after 1 year, you might be at only 99% of the capacity that you were when it was first installed. Okay, yeah, let's hop over to tutorial 2. Abhi, you want to take over?
Sure, yes. Let me show my screen with. Okay, let me know if you guys start seeing my screen.
Looks good.
Okay, cool. Thanks, Kevin. Okay, so the tutorial 3 is going to go over a very basic model called PV watts, and what we are going to do is take on the data sets Kevin went over through. So the first one is we calculated basically the plane of irradiance, and what we are going to do is we are going to take that information and we are going to calculate the cell temperature of a PV module. So as Kevin mentioned, the performance or the efficiency of a PV module is dependent upon its cell temperature. And as the cell temperature increases, the performance of the modules decrease. Oh yes, before I talk about that, let me actually also throw some light on the different level, different type of models that are out there to model PV systems. So the very basic models that are out there typically just deal with few coefficients. The PV watt model which we are going to look today deals with two coefficients. Then you can look at the electrical circuit models, which are a little bit more involved. They need more information on the modules themselves, and you'll need to basically set more parameters. And then the full-blown physics-based semiconductor models are like extremely detailed, but then they are rarely used just because you need a lot of information, plus at the same time it may not be applicable for large PV systems one models. So the increase in the accuracy may not be warranted there. Unfortunately, I'm not getting an image over here, but if you guys have your notebooks open, you will be seeing an image which is basically Mark's grandma's house, and it would be showing a PV system on top of the rooftop. So we are going to model something close to that. So yeah, as I was saying, the performance of a PV module is dependent upon its temperature, and so before we can calculate how much power a PV module is going to produce, it's important for us to understand how much what's the temperature of the cell. However, measuring the cell temperature is extremely challenging because the cell temperature is actually right in the cell. It's where the diodes are there. So typically the PV community talks about the module temperature rather than the cell temperature. And the module temperature is typically a few degrees lower, 1 to 2 degrees Celsius lower than the cell temperature. Okay, so as I mentioned, the module's power production capacity reduces as its temperature increases, and typically this is between like 0.5%, 0.5% per each degree Celsius. So 100-watt module, which would produce 100 watts at 25 degrees Celsius will probably produce 95 watts as if its cell temperature increased by 10 degrees Celsius. Okay, so going through this fairly quickly. All right, so the first, we are just importing the libraries. All right, so what over here we are doing is just redoing some of the steps Kevin showed. So we are importing irradiance data set over here, and then we are defining a location. And then you would see that in case if somebody is not familiar with the time delta operation of pandas, it just means that you are shifting your time index by a certain amount. And in this, we are shifting by 30 minutes. So if you actually, the reason why we are doing this is all the photovoltaic model simulations, or typically I should say, are hourly based simulations where you have how much, where you try to model how much power is being produced at each hour. And one of the key important inputs to do this is the sun position. Now you can imagine that the sun's position actually changes quite a lot between between two consecutive hours. So what we are doing is over here, in order to get an average sun position for a particular hour, we are changing the time index by 30 minutes. So we are bringing the index to the middle of the hour so that we get the sun position for that middle point of a given hour. All right. And then we are defining the tilt and the azimuth of the PV system we want to model. So in this, we are saying tilt is going to be 20 degrees and the azimuth is 180 degrees, which is basically facing south. All right. Then we basically take this method available in PVlib, where we just pass in the surface tilt, or like the tilt of the model of the modules and the azimuth of the modules. We also pass in the resource information, which we just read in the second line over here, and pass in the sun position. And once we do that, we can get the total irradiance that is hitting on the on the modules basically. Okay, so once we know how much irradiance is hitting the module, we can calculate the cell temperature. All right, so let's just quickly discuss why a module's temperature increases as it starts producing power. The reason is all the light that is hitting the module does not get converted into electricity, and actually a typical solar module as of today has around 20% efficiency. So the rest 80% is then converted into thermal via different mechanisms. And there's been a lot of research going on to try to improve this efficiency by reducing by increasing the conversion of light into electricity. But anything which is not converted into electricity eventually gets converted into thermal energy, and this increases the module temperature. So PVlib has some built-in models, and one of the very kind of commonly used models out there to model the cell temperature is the Sandia array performance model, which takes in a basic some basic empirical coefficients to model the temperature of a module based on how much light is hitting the module and the ambient conditions relevant to the temperature and wind speed. So over here we are just taking in the parameters which are already defined in the library, and we're just calling them using this method. And then we are using the model, the SAPM model, using the irradiance, the POA irradiance we calculated before, and the temperature and the wind speed here. I think I'm going over a lot of content over here. Do we have any questions at this point?
Nothing in the chat, Abhi.
Okay, cool. All right, so basically, just a quick recap till this point. So what we have done is we have taken the plane of array irradiance we calculated, and then we use that along with certain parameters of a module to calculate the module temperature. And just to give like quick kind of insight into like what different kind of parameters are available. These are the 4 different categories, if you will, which represents different kind of module construction. And based upon one specific module construction, you could choose one of the 4 that are available in PVlib. And this different basically parameters are nothing but a set of coefficients which you can find on the PVlib documentation. Okay. So this plot basically compares the cell temperature of the module, versus the dry bulb or the ambient temperature, if you will, across a given day or multiple days. And we can see that that the module temperature or the cell temperature is significantly higher during the daytimes when actually the module is producing power. And this is very common. The reason is, as we discussed before, that the module typically, converts 20% of the light that is hitting into electricity. So the rest, goes into actually increasing the module's temperature. So it just, goes to show how hot the modules can get. So even if you had, sub-zero temperatures, negative temperatures, your module will be still at around like 15 degrees Celsius. All right, so once we have calculated the module's temperature, the cell temperature, we are now ready to calculate how much power the system can produce. So just for this example, we'll be looking at a 1 kilowatt array or 1 kilowatt DC capacity of the of the PV system. So the DC stands for direct current, and since modules produce power in form of direct current, we just call that as DC capacity. And then the temperature coefficient is assumed to be at 0.4% per degree Celsius. That just means that your module's efficiency is going to drop by 0.4% for every degree Celsius increment, increase in your module temperature. And so PVLib has this model called PV watts already built in, which is relatively straightforward but pretty handy model to calculate how much power your module is going to produce. And so we are basically assuming 0.4% per degree Celsius of temperature coefficient and 1000 watts or 1 kilowatt of the modules installed. So this means that your modules are going to produce 1000 watt of power at your reference temperature condition, which is typically at 25 degrees Celsius. And from that point, you are going to drop 0.4% for every degree Celsius that there is in every degree Celsius your module temperature increases. So yeah, and then basically you just pass in the irradiance data set, the cell temperature which we calculated before, the nameplate which is 1000 watts, and the temperature coefficient. And yeah, this plot just shows you how much power that is generated for the given days. So if you actually compare this plot with the one above, you could see that there is a fair bit of correlation between the module temperature and the power produced. So this is the module temperature, the power produced. We can look that in more detail with a scatter plot. So yeah, this plot basically shows the array power produced versus the POA irradiance, the amount of sunlight that hit the module. So one of the obvious things is that you'll get more power as your irradiance increases, but also you can see that as your ambient temperature increases, so you'll need more and more irradiance for generating the same amount of power. Meaning if you have 800 watt per meter square at 30 degrees Celsius versus if you have 800 watt per 20 degrees Celsius, you will end up producing more power in cooler conditions, just because now that will result in cooler module temperatures. Another way to look at that same kind of thought process is to compare the array power against the POA irradiance, but this time we are actually going to have the cell temperature as the as the color coding. So we can clearly see that when the cell temperature increases, your power produced is reducing. So for 800 watt per meter square, the power produced is much less. For the same irradiance, you'll be producing less power. And then yeah, this is nothing but kind of so we basically changed the temperature coefficient from 0.4% to 0.2%. So Now, what we are saying is basically the module's performance is going to drop less, with increasing its temperature. So meaning you get, like a thinner distribution, if you will, of the scatter plot. So your module's temperature is now less affected by, or your module's performance is less affected by its temperature. And yep, and this plot is showing how much production you get for given POA. You might notice that the production is actually higher for certain months, even if the POA is lower, and that is typically because the temperatures are cooler in these months, and so your modules will be actually more efficient than than their standard conditions. So you'll end up getting more power. So it kind of helps smoothing out the profile, if you will. So basically, doesn't mean that if you have high POA, you'll always get more power. The temperature also plays a significant role. Yeah. Any questions so far?
Yeah, there are two great questions.
Yes.
One person asked, like, what is the max temperature difference from ambient that a PV panel could experience?
Oh, good question. I don't know. Probably I've seen field data with module temperatures as high as 70 degrees Celsius, 70, 75 degrees Celsius. But yeah, Mark, do you have any?
I mean, for normal environments like where we live, I would expect a 25 degree C difference between ambient, and operating temperature, because, panels.
Yes.
Yeah. But I mean, I've seen in Las Vegas, I mean, I don't know how hot, I'm bad at Celsius, but in Vegas or Phoenix or something like that, panels could get up to 75 C. So that's quite a big jump from ambient,
Yes. So yep, exactly. So I was talking about the module temperatures, and I've seen them to be 70, 75 degrees Celsius. So if your ambient temperature at that point was around, let's say, 45 degrees Celsius, then you would be seeing around 25, 30 degrees Celsius difference.
Yeah.
So yeah, the modules can get really hot.
Another question somebody asked was, are there certain actions you can do to, I guess, respond to this temperature rise in the panels? Interesting question.
Yeah, I mean, so there's actually not much of research that has happened in that direction, and so that there are two things you could do. One is look at passive cooling. Passive cooling would probably mean that now you need to add some kind of fins in your modules, and also probably get your modules exposed to more windier conditions in a way. But typically the costs associated with such techniques are kind of quite high, and they may not warrant it's I think it's a good question, but there's not much one can do. Now, of course, if you look into active cooling, that is completely different kind of ball game. You'll have significant drop in temperatures, but I think the costs would be just prohibitive. That's my first reaction. But yeah, maybe in space applications, yeah, they may be having active cooling just because it's a very specific system, and over there they can, I think, cost and all that is kind of less of a variable.
Abhi, in my experience, the only time I've seen any kind of passive cooling on PV, it was a concentrator.
Okay.
So SunPower used to have a 7-sun concentrator, And on the back of each module, they had fins, just like you said. And then the way that concentrator was designed is it had, I don't know, several different panels that were on these curved, at the bottom of like a curved mirror that focused on it. And so they, the way the air flowed through those, it was a tracker and it tracked the sun. The way the air flowed between those curved mirrors, kind of like it was designed to have like an airflow that was accentuated by the curvature of the mirrors, and then it would go through those fins. It was kind of a cool design, but they hit the exact issue that you're talking about, like the cost, the marginal increase of cost kills the whole thing. So, and I haven't to date, and I've been in solar for a little bit of time. Maybe there's people with more experience who have seen something successful, but I haven't yet seen anything successful.
Yeah.
But there is one cool thing. What about floating voltaics, right?
Yes.
Floating voltaics seem to run about 10 degrees cooler, right?
Correct.
So maybe that's the one, I don't know, thing.
Yeah, definitely. Yeah. So I think, just for everybody. So floating voltaics is basically, a system which is constructed on top of a water body. And, that there are, a few different ways you could place them. You could directly place them on a floating structure, or you could, have a rigid structure supporting the PV system. But I think the idea Mark is talking about is basically having water underneath those PV systems, which would have a significant cooling effect compared to the PV systems on the land.
Abe, sorry, apologies for the interruption. I just want to let you know that we have a few minutes left.
Oh, sure. Yes, thanks.
A little under 5 minutes.
Okay, cool. All right. We have just 2 more cells to go over. So sorry, I'll take on the other questions after I go over this couple of cells. So far what we saw was, we basically modeled how much power that the modules are producing. But as I said, the modules produce power in form of DC. And as you would know, the power we use at our homes or, any kind of grid applications, most of the power is, AC is in form of alternating current. So there's a component called inverter, which takes the power from modules and converts that into, AC. So we need to convert DC into AC. And that means, we need to model the inverter as well. Now, typically we actually put more capacity, quote unquote capacity on the inverters, so that, any efficiency loss the inverter will have will be, kind of covered by this more capacity we have installed. There are, a few other reasons as well why one would put more module power on top of an inverter, but I think we are short of time, so excuse me for not going into that detail. But PVlib has this inverter model in there where it takes the array power, which we just calculated in the cell above, and then the inverter efficiency, excuse me, which is a static number in this case. And so finally what we get is basically the AC power your PV system is going to produce, and this is showing how much energy your system produce in a given day. And so the blue one is the AC, which is the output of the inverter, and then the orange one is how much the modules produced. And as you see, the efficiency of the inverter, kind of taking out some power. But yeah, and then I would say this is just like a very gentle introduction to PV systems, and there's really a lot more one can do. With PVlib, like PVlib has amazing methods already built in, and it's super powerful to do a lot more. So really cool stuff can be done using PVlib. So yeah, I think I'll stop there and probably just take on any last minute questions we have.
So I posted in the chat there's a link to a survey, a Google survey. If everybody could, if you have time to click and give us some feedback, that would be really fantastic and helpful. And then we'll stick around on the Slack channel, which is the Data and Tools to Model PV Systems. And everybody should have access to Slack. So for me and everybody, I just wanted to thank you all for joining. I hope you learned something about PV and give it a try to model it. And thanks.